Okay, we're going to finish up the types of reactions with redox. It says oxidation reduction, but most people just call it redox for short. Okay, redox is actually really important because, especially biologically, because our body does oxidation reduction all the time. Whenever we eat, the food that we're digesting becomes oxidized in our stomachs, and it gets absorbed into our system. And that's all because the food is breaking down. The electrons are switching places. And then that gets absorbed into our cells. So it actually has a very big biological function. Now, you notice in the last section, we talked about different types of reactions. There was 5 different types of reactions. Well, in reality, redox essentially happens in all of those. So that's why they've categorized it as its own thing. Now, in order to actually teach you how to do a full redox reaction with balancing electrons and whatnot, it would take a very long time. So instead, we're just going to be able to point out which one's being oxidized and which one's reduced. Now, I keep using these terms oxidized and reduced, and you're probably confused right now because we haven't defined them yet. Well, whenever anything happens, for instance, here we have iron by itself, and so that's an element. It's elemental iron. And then it's getting bonded with the oxygen. Well, anytime a bond occurs, it can form 2 different types of bonds that we've talked about, and that's covalent or ionic. Covalent, the electrons are being shared. Ionic is a give and take. The metal's giving it away, the non-metal's taking it. Well, as a result, because of the fact that there's this give and take involved, the electrons are being switched over. They're changing forms. The fact that, and that is what redox is all about. Redox is all about one electron going from an electron going from one place to another place. For instance, the electrons from the iron are being transferred over to the oxygen to make this compound. And that transfer of electrons is what redox is. And we're going to break down how we know if it's an oxidation and how we know if it's a reduction and what to look for. Alright, so when we're looking at redox, here we have an electron on top of the atom A. Notice that they put the electron on the outside. These are the valence electrons. In the middle are the core electrons. The core electrons don't react. It's only the valence electrons that are reacting. And the electron is moving from A to B. So you notice on the right-hand side, the electron is with B now. That means that A lost an electron, and B then gained that electron. Anytime an electron is lost, it has to be gained somewhere. It has to go somewhere. And that's what redox is trying to determine, is who's giving, who's taking. Now, there is actually a mnemonic device for this. It's called Leo-Ger. Lose electrons, oxidized. Leo. So that means when A lost its electron to B, it was oxidized because it's a loss of an electron. And then Ger is gain electrons, reduced. So B gained that electron that A donated. So here's that electron now. It gained the electron. It was reduced. Let's break this down a little bit further and look at the charges. A had a negative charge and it gave it away, so it became more positive. B gained that electron, so it became more negative. And you should be able to look at the difference in charges and determine if it was oxidized or reduced by just looking at those charges. They use a different mnemonic device. If you want to use the oil rig, that's fine. I find Leo Gurr, just simply because that was the first thing I learned, to be simpler. Okay, let's take a minute to look at your periodic table. So if you do not have your periodic table out right now, pause the video and get it out. You will notice that your periodic table is broken into different rows, different columns. Each column, the elements, especially the tall ones, typically have a charge that they obtain. It's not going to be 100%, but it gives you a roundabout. -2, -1, 0. So for instance, hydrogen, that row is a +1. Beryllium, that row is a +2. Boron's a +3. The carbon row you're going to skip. And then it's nitrogen is a -3. Oxygen's a -2. The row that begins with fluorine is -1, and then the last row is 0 because they don't really react. They don't share the electrons. Now, if we have a squiggly line determining the metals and nonmetals, the metals are positive, and the nonmetals are either negative or variations of negative. It's not going to... If it's a nonmetal and a nonmetal, it might not be these exact charges all the time. You'll need to know this information, especially the positive and negative. Those are the ones that are most important. Because I'm not really looking at how many electrons are being transferred. I'm more concerned if whether or not you can identify where the electrons are or where they're going to. For instance, who's gaining and who's losing. So, if it's with something, like copper is with oxygen right now, if it's with something, you're going to use these charges up here. If it's all by itself, or if it's bonded to itself, and not, notice oxygen is with copper here, but oxygen is just by, oxygen is with oxygen here, it's not with a different element. Those are called elemental atoms. And those will always have a charge of 0. But if we look over here, when copper is bonded to oxygen now, it's bonded to something, which means we're going to use these charges. Oxygen is right here, that's a -2. Copper is right here, so we know it's going to be positive, but it's a transition metal, so we don't know what it's going to be positive of. Well, that means if oxygen is a -2, that means copper has to be a +2. So that means copper is going from 0 to +2, and oxygen is going from 0 to -2. So if we look at the number grid, here's 0, this is +1, this is +2, +3, this is -1, -2, -3. Copper started here, and it became a +2. It became more positive. Well, electrons are negatively charged, and so if you lose electrons, you're going to become more positive. So it became more positive. Means that it lost electrons. And if we remember Leo Gurr, lose electrons, oxidize. That means that this copper was oxidized. If we look at oxygen, we go from 0 to -2. Here's 0. It went to -2. It became more negative. That means it gained electrons, because electrons are a negative charge. So that means they added more electrons to that atom. gain electrons reduced. Let's try some more. So we have 10. It's not bonded to anything, and there's no charge, so that means it's a 0. It's going from 0 to a +4. So if we look at our number line, here's 0, +1, +2, +3, +4. It went from 0 to +4. It became more positive. Which means that it lost electrons. So if we look at Leo-Gur, lose electrons oxidized. That means this was oxidized. Iron went from a +3 to a +2. It started off here and went to here. It became less positive. Which means it gained electrons in that process. Because it gained negative. So, gain electrons reduced. Okay, chlorine. It's a 0 here because it's bounded to itself. It's elemental chlorine. And it's going to a -1. So it started off 0 and we're going to a -1. Became less positive or more negative. Because those two are the same thing. That means it gained electrons. So gain electrons is reduced. Now that's one basic definition of redox. Here's another example. It's going from a positive. It's not bonded to anything and it doesn't have a charge up here, so that means it's a 0. It's going to a +1 to a 0. So if we look at our number scale, here's 0, +1, +2, -1, -2. We started here, and we're going to 0. It's becoming more negative. It's going further to the left. That means it gained electrons. So if we look at Leo-Gur, gain electrons reduced. That means what's reduced? It would be silver. So if we look at chlorine, it's going from a negative this time to a 0. So we started off here and we're going here. It's becoming more positive. Which means we lost electrons here. Lose electrons oxidized. So that would be chlorine. Alright, that was one example, one definition of redox. There's actually a biological definition of redox, and that's where these terms actually come from. It's referring to the oxygen. When we talk about biological functions, they transfer either hydrogen or oxygen. So if we're looking at oxidation, you're either adding oxygen or we're losing hydrogen. We're talking about reduction. We're talking about adding hydrogen or losing oxygen. So notice that they're reverse of each other once again. But at the very basis of redox, when they first started realizing what redox was, they were interested mostly in biological functions. So Here, if we're looking at it, here's some hydrogen atoms here. Then we have the coenzyme FAD here. These hydrogens are being given up to the coenzyme right here. Because this coenzyme gained those hydrogens from that molecule, it's being reduced. If you add hydrogens, it's reduced. Whereas here, oxidation, you lose the hydrogens. Losing hydrogens is oxidized. So this particular definition relies more on the biological sense of just looking at oxygens and hydrogens and less of looking at specific charges. So if we actually broke down those definitions, oxidation, you lose the electrons, and reduction, gain the electrons. Those are the very specifics. Now, it may, notice the word may, because it's not always 100% true, but they realized it was a trend in biological functions, that if it's oxidized, you're usually adding oxygen, or you're losing hydrogen, one or the other. And then the reverse is true for reduction. You're losing oxygen or you're gaining hydrogen. So if we look at methyl alcohol, in the reaction form formaldehyde. Notice it starts with CH3OH. We still have the C and the O, but we have 2 of the H's now rather than we have 3 and 1 here. So there's 4 here originally, and now we only have 2. Well, here's our other 2. So we lost the hydrogen off of this original compound. That loss of hydrogen means that it was oxidized. If we look at formaldehyde to formic acid, H2CO, H2CO2, we added an oxygen here and went from 1 oxygen to 2 oxygens. That addition of the oxygen makes it oxidation. So it's looking at the flow of the oxygens and hydrogens, not specifically the electrons. The electrons are actually the more correct way of looking at reactions for redox. However, this is the biological way of doing it. And that is the end of section 6.